Okay, in the last class, we started by solving some simple logs equations. In this one, we're going to find some more complicated ones. So, for example, let's look at this first one. You can undo the product property by making this go back into a multiplication. So, doing that, I get log of x squared plus 3x equals 1. Okay, so my goal is to find my x. So change the form. Since there's no 10 here, this is base 10, logs equal exponents of 1 equals x squared plus 3x. So you need to recognize that as a quadratic. When you solve a quadratic, in this situation, we have two answers. Now, you have to consider whether you can use the answers. So 1 is -5. Go up and try to put a -5 right here, and you find yourself taking the log of a negative, which you cannot do. Because that happened here, I have to reject that answer. Check this one, because there's no guarantee that a positive answer is going to work. If I put 2 here, I'm okay. If I put 2 here, I'm okay. Had this been x minus 3, I could not have used 2 either, and I would have rejected both. So just be aware that you want to check both of your answers. So in this situation, we can only accept one answer, and that's x equals 2. So next we talk about the uniqueness property as it pertains to logs. So remember, if you have the same base, you can set the exponents equal. Well, if you have the same log of the base, then you can set the arguments equal. All right, so we're going to work on that now. So it says solve for x and check your answer. So to have this on the left equal this on the right, since they're both base 10, you can set the arguments equal, and you're going to solve for x. I get x is 3. When I plug x over here into 2x minus 3, I'm positive, so I can accept that answer. Okay, this next thing is a pretty interesting SAT type problem. So look how we're going to handle this. On the left side, you have an expression that's in log base 2. On the right side, it's an unknown base. So take the left side first and undo the quotient property. That makes the left side log 2 of 24 over 3. And that has to equal something. So I just said it has to equal x, just for my purposes here. So now let's do this division. 24 divided by 3 is 8, so that's good. Next thing, I made 8 into 2 to the third because I recognize I'm going to have a base of 2 here, and I know that's going to make my life easier. I can then rewrite my function as an exponential function. My base is 2, logs equal exponents. X is 3, so that means that the left side is 3. So now step B takes place. Set the right side equal to 3. Now when you do that, it should trigger in your mind that, wait a second, isn't 27 3 to the third? So if that's the case, then that's going to help me. So let's keep working through this. Rewrite it in exponential form. So x to the third equals 27, because logs equal exponents, and the argument goes here. So how about turning 27 into 3 to the third? I have the same exponent now. So for these two expressions to be the same, x has to equal 3, and that's our answer. So you want to go back and just think about that, because I think that's a very interesting problem. Okay, moving on. The general method for solving logarithmic equations. So I have two things I look for. If I see I have log equal log, then I use unique log and get my answer that way. If instead I see I get log equals number, I then change the form into an exponential problem. So read through this, make sure that makes sense. And now what we're going to do is look at our problem down here. Again, I focus on the addition. That means in a prior life it was a multiplication. So do that multiplication. 6 times x minus 1 That gives me natural log of 6x minus 6 equals natural log of 3x. Because they're both natural log, the uniqueness property lets me set 6x minus 6 equal to 3x. And doing that, I get, as I move things around, I'm going to get x is 2. Look at all my steps. Take that 2 and plug it back in wherever you have an x. Make sure it doesn't go negative. It doesn't, and therefore I can accept 2. Okay, my next example here is a situation where I have log plus log equals a number. So since it's log plus log equals a number, then that means what I'm going to do is see if I can get this form to change once I undo the product property. So 3 times x minus 7, that's 3x minus 21, is going to equal 2. So 10 squared, why did I say 10 squared? Because I'm changing the form, and there's no number here, so the base is 10. So 10 squared, because logs equal exponents, equals 3x minus 21. So square the 10, you get 100. 100 equals 3x minus 21. Add 21 to both sides. Divide both sides by 3. And you end up getting x equals 121 over 3. Now that is a little bit more than 40, right? Because 4 times 3 is 12. So it's about 40. If I use a 40 here, I'm okay. It does not go, the expression, the argument does not go negative. Therefore, I can accept that value. Okay, let's go on to some more. All right, so next ones, we see that I have log on both sides of the equation. So my strategy is going to be to use unique log. This is a subtraction, therefore that was a division, undoing the property, and I get the left equal to the right. Now, because I'm into unique log, you are allowed to set these guys equal, and I'm going to do cross products to get to my answer. Okay, so doing our cross products reveals I have another quadratic to work with. So when I combine all my terms, just look at all these steps. Here's my factors. So again, since we're factoring once more, if you are not a good factorer, you want to work on that because that's going to help you to be successful in this section. So look what I have. I have a negative 7. When I plug in negative 7 in the denominator, this goes negative. So therefore, I can't use it. It goes negative here too, by the way. So I'm rejecting this on 2 different grounds. When I plug in 2, I'm okay. So I can accept the 2. Okay, let me just slide this up for a sec. All right, so here we have log equal number. So our strategy is going to be to change the form and make it an exponential function. So take your base 4, logs equal exponents, raise it to the squared, and that equals the argument. Isolate your x variable, and your answer is 26. When I plug in 26 here, I'm good, so I can accept that. Okay, so here's another thing we're going to talk about. If you are dealing with an x in the exponent, then one of the strategies you can use is to take the log or the natural log of both sides and then work it from there. When I do that, and I also do the power property, I can bring this exponent down in front, and therefore that helps me to isolate it. So here, log of 8x equals log of 792. Doing it on both sides makes it a legitimate algebraic operation. So my goal is to isolate my log. Here I have log 792 over log 8. That is an exact answer. We're looking for approximations to do 2 decimal points. Put this in your calculator just the way you see it, and you should get 3.21. Same thing over here. You're going to take the log of both sides while also using the power property and bringing the negative x in front. Okay, in order to get rid of the negative then, because you're going to be left with a negative x once you divide both sides by log 2, what you're going to do is multiply both sides by -1 because I don't want negative x, I want x. And when I do that, and I put this in my calculator, I should be getting 4.47. So check to make sure that you're getting this. Okay, next one. Once again, the x is in my exponent. I'm going to use the fact that I can take the log of both sides. When I do that and do the power property, I get x plus 1 in front. Why don't you go ahead and put that in paren so that you don't think that it's just an x and then a plus 1. This is a combined term. Divide by log 2. Isolate your x by subtracting 1 from both sides. Put this in your calculator, and you should be getting 3.91. Okay, so next one. So since I have, let's see what I'm doing here. Since I have natural log, I'm going to take the natural log of both sides and also bring this down. So the natural log of e is 1. Okay, so look down here, I did this little operation to prove to myself that the natural log of e is 1. Okay, I changed the form and found that x equaled 1, so this expression goes away. I'm left now with just x minus 1 on the left side, and then I'm going to add 1 to both sides, and I've divided by natural log of e, correct? And that's just 1, so therefore my answer is going to be the natural log of 15 plus 1 is the exact answer, and 3.71 is the approximation out to the 100th. Okay, so that brings us to more practice. So we did not do all of these in class, but I have them all done here for you. So what you're going to do here is I see that I have natural log equals a number. So my goal is to change the form. So look what I've done. I have brought the 7 over as a negative. That cancels out the 7 that was already there on the right side. I have a 0. Divide both sides by -2. That still gives me a 0. Then use your ability to change the form by saying e to the 0 equals x plus 1. Remember, anything to the 0 is 1. So subtract 1 from both sides, and you get x equals 0. Now, can you use x equals 0? Well, let's see. Plug it in over here, and that works out fine, so I can accept that. Okay, problem 2 is going to be log equal to log. So my goal is to get unique log. And here I undo the product property by doing a multiplication. That's done. Now I have log equal log. So you can set the arguments equal, recognize that as a quadratic, bring the 8 over as a negative, and factor. You get 2 answers. The -4 gets rejected because if I plug it in the very first term, it requires me to take a log of a negative, which I cannot do, so I reject that. Let's check x equals 2. X equals 2 is good there. It also is good there. I can accept it. Okay, a couple more to do. Okay, look at 3. That's going to be log equal to number. And that means that I'm going to end up changing the form to get my answer. So first, undo this quotient property by making this a division. And then what I'm going to do is change the form. So 2 to the 3 equals this. 2 to the 3 is 8. So 8 equals this fraction. Cross multiply, you get 8x minus 16. Don't forget to multiply the 8 times the 2. And that equals x. Bring your x's to one side and your numbers to the other side, and you get 16 over 7, which is more than 2. I needed to know that because if I put it in here and it was less than 2, I'd have to reject it. But I can accept it, so we're good to go. Okay, number 4 is a log equal log situation. So undo the product property and multiply 3 times x minus 2. You get 3x minus 6 as your argument. And then on the other side, you've got the 5x minus 7. Set those two arguments equal, And when you do that, isolate your x. You get x equals 1/2. And look, if I plug in 1/2 here or here, everything goes negative, and I can't do that. So there's actually no solution to this problem because I've got to reject my answer. Okay, so these are the last two. So what I'm going to do here, because my x is in my numerator, is in my power, I'm going to go ahead and take the log of each side. So I take the log of each side, and doing that gives me two things in base 10. So then log of 10, by the way, equals 1. You can prove that for yourself. So I have x over 2 equals log of 1/2. So isolate your x. X equals 2 times log of 1/2. That's about negative 0.602, and that's my answer. So I'm good there. And then this last one, what I did first was I divided by 10. I then had e to the 2x equals 40. And it was pretty easy just to change that form. Did I do that? Let me see what I did. Yes, I did. So natural log of 40, which is the argument, equals the power. So now my goal is just get x by itself, divide by 2, and I get x is 1.844. I could have taken the log of both sides also, and I would have gotten the same answer there. So I hope this helps you with this section, and I'll see you in class.